Sorry, Steve, can you just announce the next talk? I haven't got the schedule open right at the moment.
Yes, I do have it, although I hit it. The first talk is from Jeyhan Kartaltepe on the COSMOS-Webb program, and the title is COSMOS-Webb, the Webb Cosmic Origins Survey.
Thanks, Steve.
All right, I just shared my screen. Hopefully everybody can see that. All right, good morning, good afternoon, good evening, everyone, whichever time zone you happen to be in. Thank you all for joining for the first session of this meeting, which I think should be very interesting. And I'm very happy to be starting off the session about JWST because many of us have been spending many, many years thinking about JWST and what we want to do, and really our dream science that will be done with this telescope. And we've spent a good chunk of this pandemic thinking about JWST and writing proposals. And so, I share with what Steve said earlier that I think a lot of us were pleasantly surprised by the results of the TAC and how much extragalactic science really came out of that. I think it's recognized that we need to do a wide variety of surveys early on in the Webb lifetime in order to study all of the things we want to study. So I'm going to kick it off by talking about COSMOS-Webb, the Webb Cosmic Origins Survey. So this is a survey led by Caitlin Casey and I, along with the Cosmos team. So I'm going to jump right in and give you the details about the survey. I think this is the piece everybody wants to know. What are we going to do and what data will be available? So COSMOS-Webb is a 208-hour program, and we're going to cover 0.6 degrees with contiguous NIRCam observations in 4 different filters, which are listed here: F115W, 150W, 277W, and 444W. The depth ranging from about 27.5 to 28 magnitudes. In parallel to that, we're going to have MIRI observations in a single filter, F77W, covering 0.2 square degrees. Now, because of the parallel field layout and our prioritization over the NIRCam coverage shown here in blue on this map, the MIRI observations won't be completely contiguous. Instead, the MIRI observations are going to be in stripes across the field, with most of them overlapping with the NIRCam coverage. I think the main thing that we really want to highlight and that I want you all to take away from this talk is that this survey is intended as a community legacy survey, right? Like all the other large Treasury programs, the raw data will be public immediately, but we're also committed to releasing our data products quickly and efficiently so that the entire community has this data set to start looking at, to start playing with, and to be planning their own follow-up observations in the future. And so this figure highlights our coverage, so 45 by 47 arc minutes in NIRCam with the MIRI strips shown in red, and with the candles field overlaid to give you a sense of scale. I think a lot of people are familiar with the candles coverage in Cosmos, so that helps to give you a sense of scale there. All right. So COSMOS-Webb has 3 main science goals that we want to accomplish with this data set. The first one here is the one that's most relevant for this conference, and that's to identify thousands of galaxies in the epoch of reionization, spanning from redshift 6 to redshift 11, mapping their spatial distribution. So this is key for a survey like COSMOS-Webb. The large area contiguous survey allows us to study their environment, quantify their environments and the level of clustering for these EOR sources. And then we can investigate their physical properties relative to the environment with which they're in. The second main science goal is to identify and characterize rare quiescent galaxies in the first 2 gigayears of the universe, so Z greater than 4. And the third is to directly measure how the stellar mass to halo mass relation evolves with redshift out to a redshift of 2.5, and then explore how it varies with certain galaxy properties. And so we're going to spend the most time in this talk talking about the first science goal, of course. And I also want to point out that beyond these 3 key science projects that our team initially proposed, there's really an infinite amount of science that you can imagine doing with a data set like this. And so we hope that the community will be ready to jump on this as soon as possible. When we planned out this survey, right, the need to have a contiguous area to study the clustering of reionization sources, and for the lensing measurements that we're going to make for the stellar mass to halo mass relation, really led to the COSMOS field being the ideal choice for such a survey. So we needed a large area field that has extensive and near uniform ancillary data. So COSMOS has existing X-ray through radio observations. There's existing HST F814W observations, which are really essential for optimizing our redshift 6 to 7 galaxy selection. There's a large number of UV optical IR bands that already exist in the field that have provided superb photometric redshifts and will really help to leverage the JWST filter set for photometric redshifts at higher redshift. And there is extensive and constantly growing spectroscopic coverage in the field. I think in recent years, the COSMOS field has really become an area that a lot of people have targeted for their own spectroscopic follow-up. And so in parallel to this, another program that we currently have going on is to collect all of that ancillary data, including archival observations that haven't been looked at or published, and put them all in one place for the community to help enable science that can be done with all of that spectroscopy. COSMOS is an equatorial field, which is essential to optimize follow-up. That means every major ground-based telescope on Earth will be able to follow up sources that COSMOS-Webb identifies. And in particular, accessibility by ALMA was something we felt was really important because we'd like to be able to use ALMA to follow up sources identified by COSMOS-Webb. And COSMOS has been selected or is likely to be selected as a calibration field for many future projects in future surveys. So this seemed like the ideal place to put a survey like this. I want to point out the complementarity. So in the next few talks, we're going to hear all about different surveys that are going to be done with JWST. And I think it's really important to acknowledge that in cycle 1, James Webb will image several tiers of the extragalactic wedding cake. So in cycle 1, we're going to have immediately at our disposal data spanning large areas to small areas, shallow data, deep data across the entire range, which is very exciting. And in addition, there are many targeted programs looking at specific objects and peer parallel programs, which you'll hear more about. So I want to highlight the depths of COSMOS-Webb. So this is a magnitude versus observed wavelength plot that shows all the different filters that are currently available in Cosmos, and then in orange are the filters that we're going to cover with COSMOS-Webb. And so you can see the relative depths of those here to a few different templates. And so surveys like Sears and Primer, the depths would be at the bottom of this plot, and surveys like Jades and W Deep are really off the edge of this plot. So this really highlights the complementarity of all of these different surveys in terms of their area coverage, their depth, and their filter coverage. All right, in COSMOS-Webb, we expect to detect about 4,000 to 5,000 galaxies at redshift 6 to 8. About 70 to 85 of those we expect to have MIRI detections. And then we expect to detect about 500 to 600 galaxies at redshifts 8 to 10. About 10 of those hopefully will have MIRI detections. And we expect to detect 30 to 50 at Z greater than 10. And I want to point out that because of the relative shallow coverage of COSMOS-Webb, these are all going to be toward the brighter end of the luminosity function. So they're going to be very complementary to the objects that other surveys are going to be finding. But this will allow us to really constrain the bright end of the luminosity function and the stellar mass function to Z greater than 8. The wide area coverage means we can investigate the clustering of these EOR sources. So we're going to construct density maps in several high redshift bins in order to investigate how clustered and how well these sources trace reionization in the early universe. And we expect to spend a lot of time on future follow-up observations. And so the fact that we're going to detect a lot of bright sources will enable efficient follow-up from ground-based telescopes such as Keck in the VLT, and from ALMA for spectroscopy. We, of course, expect that there will be future cycle JWST programs to follow up sources, and as well as future Hubble imaging, which will allow us to identify Lyman alpha emitters and constrain the physics of these sources, constrain the ionizing photon production, their IgM neutral fraction, their metallicity, their dust content, etc. So all of the details that we're used to studying about low redshift galaxies we'll be able to do for these EOR sources in the future, which will be very exciting. All right, so this diagram shows the area coverage. Sorry, I'm distracted there. On the left here and in the upper right are cosmological in-body simulations showing what we expect to detect from an area like COSMOS-Webb, which is highlighted in white. And so the pink areas show the ionized hydrogen gas, and the blue areas show the neutral IgM. And so the galaxies we expect to detect with COSMOS-Webb at our depth are shown by the black dots. And so this shows that the clustering that we expect to see is on the order of the 10 to 40 arc-minute scale. So we need an area of this size in order to detect this level of clustering. In the middle and the bottom here is a reconstruction of taking these mock galaxies and deriving density maps for those to show how well we can actually identify these structures. Okay. I'm not going to spend time on our other two science topics, but feel free to ask questions if you have any. COSMOS-Webb will detect rare quiescent galaxies at Z greater than 4, and our filter choice was really optimized to separate quiescent systems from dusty star-forming galaxies. So we really expect to be able to constrain the density of high redshift quiescent systems and constrain theoretical models. And finally, we will study the evolution of the stellar mass to halo mass relation by conducting a careful weak lensing analysis in the field. This diagram shows the observed evolution from HST observations in the cosmos field, and we expect to be able to push this out to redshift 2.5, as well as look for variance with properties such as galaxy morphology and color gradients, which will allow us to test various quenching models. So in summary, COSMOS-Webb will provide a contiguous large area multi-filter data set in cycle 1, which will enable the science I talked about here and many, many other science projects beyond that we hope the community will become involved in. Follow-up observations will be crucial for reionization studies, and we hope that this data set will be invaluable to the public. And I'll end there, and I'm happy to answer any questions.
Thank you very much, Jeyhan. And remember, if you do have any questions, then please put them in the Slack. We're just going to have a roughly 30-second breather while we give people the opportunity to put questions in. So if you do have any questions, do put them in. And we'll come back to the questions in about 30 seconds. Going to see how awkward these pauses are. We thought they were a good idea.
Jeyhan, I'll give you the first one. So we have a question that asks, will there be public catalogs with all the ancillary photometry based on a NIRCam source catalog?
Yes, so that is our plan. So we will be, based on our NIRCam data, measuring the photometry and all of our other data and producing a catalog that's matched that way. That might be a little bit longer time scale from some of the initial releases, but that is our plan.
And our next question is, I'm sorry, I'm going to paraphrase this a little bit. Do we have any quasars in this field, particularly redshifts greater than 6? And
yes, we do.
Do you know how many we have?
I do not know offhand. I would have to look that up. So I'm not sure exactly how many there are, but there are a number of known high Z sources and high Z structures in this area.
Excellent.
Okay, so a good follow-up to that one. Somebody was asking specifically about the protocluster at redshift 6.9 identified in the logger survey. Do you happen to know if that is included in your area?
Yes, so I believe that one is just slightly off the edge of the area.
Okay.
Yeah.
Right. There is one more question in the chat, but we've just run out of time. So if Jeyhan, you wouldn't mind answering that one in Slack, that would be great.
And people can continue to ask questions of Jeyhan and of all the speakers in their respective Slack threads.